Welcome back. We first defined the center of a group. Let's let G be a group. The center of the group G is the subset of all elements in G that commute with every element of G. That is, Z of G denotes the center of the group G, and it is the set of all elements A in G such that A x is equal to xa for all x in G. So in other words, A belongs to the center if A commutes with all the elements of the group. Now the centralizer, again G is a group and A is an element of G. The centralizer of the element A is the subset of elements of G that commute with A. That is, the C of A denotes the centralizer of A. It is the set of all x in G such that xa is equal to ax. So x is in the centralizer of A if x commutes with A. So I'm going to leave. I'm going to let you go ahead and try to prove that the centralizer of a group, centralizer of an element A of a group is a subgroup of G, and then the center of G is the intersection of all intersection of the intersection of all the centralizers of elements of G. I'm going to go ahead and prove the theorem here that the center of a group G is a subgroup of G. So let's do that. The center of a group G is a subgroup of G. First of all, the identity belongs to okay, so I have a typo here. This should be Z of G here. So I'm claiming that the identity belongs to the center of G because by definition, the identity commutes with all the elements of G. So so the identity E in G, okay, so I think I don't have a typo here. It's just the way I'm saying it. The identity E in G, by its definition, commutes with all the elements of G, and so E belongs to the center of G. We now show that the closure property holds in Z of G. So let's let xy belong to Z of G. To show that xy belongs to the center, we have to show that xy commutes with all the elements Z in G. Well, let's look at this. So so if I multiply xy with Z, by associativity, I have x. I can regroup these factors. So x times yz, and then since y is in the center, so y commutes with any element. So yz is the same as zy, and then I can regroup again. I can write xzy. And then x is in the center, so x commutes with z. So xz is the same as zx. And then I can regroup here again. I can write z times xy. So xyz is equal to zxy, and this is for any z. So we see that xy commutes with all the elements of the group, and so we see that whenever xy is in the center, x times y is also in the center. Okay, so this establishes the closure property. And the last thing I want to show is that if x is in the center, then the inverse of x is also in the center. So to show that x inverse is in the center, we have to show that x inverse commutes with all the elements of the group. So let's say y is an arbitrary element of G, And since x is in the center, we know that y inverse times x is the same as xy inverse for any y. And so now what I'm going to do is I'm going to take the inverse of each side of this equation. So y inverse x inverse is equal to xy. So the inverse of y inverse x is the same as the inverse of xy inverse. Now we know that this would be equal to the left hand side here would be the same as x inverse multiplied by the inverse of y inverse, but the inverse of y inverse is y. Here we get the inverse of y inverse, which is y, multiplied by x inverse. And so we find that x inverse y is equal to y x inverse. So we see that x inverse commutes with any element y of the group G. So we see that if x is in the center, then the inverse of x is also in the center. I have a typo here. It should be x inverse. So x inverse is also in the center. So we have shown that the identity is in the center. We have shown that the center is closed under the operation, and we have shown that we have shown the existence of the inverse of each element of the center. And in other words, the inverse of any element in the center is also in the center. So therefore, Z of G is a subgroup of G. Okay, so now the order of a group. So what do I mean by the order of a group? The order of a group is basically the number of elements in the group. We use the notation absolute value of G to denote the group order. So what's the group order of Zn? Well, in Zn we have n elements, so that's the order of Zn. What is the order of Zn star? Well, how many elements do I have in Zn star? And if you recall that we have phi of n elements in Zn star. And what is the order of the group of integers? Well, that's infinite because there are infinitely many elements. The order of R star is also infinity. So if the group has infinitely many elements, then we say that the group has order infinity. Okay, so this would be a very key definition. Let G be an element of the group of a group G, and then the order of the element G is the smallest positive integer n such that G to the n is E. In the additive notation, we would write Ng is equal to E instead of G to the n is equal to E. Now, so basically we are saying that the order of G is the smallest power of G, smallest positive power of G that is equal to the identity. We use the absolute value around G to denote the order of the element G. If for every positive integer n, we have that G to the n is not equal to the identity, then we say that G has infinite order. Okay, so Z15 star has the following elements. So these are the elements that are relatively prime to 15. So these are the only elements that have multiplicative inverses in Z15. And this is a group under multiplication mod 15. What's the order of this group? Well, the order of this group is how many elements we have in this group. So 1, 2, 3, 4, 5, 6, 7, 8. So the order of this group is 8. Now, what's the order of the element 7? So now I have to figure out what is the least power of 7 that is equal to the identity 1. Well, if you calculate, you'll see that 7 to the 1 is 7. 7 to the 2 would be 49, and 49 modulo 15 would be 4, and 7 cubed. So 7 squared would be 4 in this group, and 7 cubed is going to be 7 cubed is going to be 7 squared times 7, which would be 4 times 7 or 28, and modulo 15, that's going to be modulo 15, that's going to be 13. And then 7 to the power 4, so if you calculate 7 to the power 4, that's going to be 91. So that's going to be 7 cubed times 7. 7 cubed is 13. 13 times 7, that's 91. And 91 modulo 15 is 1. So we see that if you calculate powers of 7, you'll see that 7 to the 1, 7 to the 2, 7 to the 3, and 7 to the power 4 is the first positive power of 7 that gives you 1. So the order of 7 would be 1. So the fourth power of 7 is the least power of 7 that gives you 1. So the order of 7 would be 1. Okay, so you can find the order of 11 in the similar way, and so on. Okay, so this is it. This is all we have on this video, and that's the end of my discussion on subgroups.